I hit record and I'm not fucking ready because that's the master fucking Jedi I am. Math 21, day 12, lecture day 10. We're going to continue with 5.5. 5.5 was on the counting techniques. Remember we did the lightning, or not lightning plates, the license plates. God, I'm all fucking flustered. We did lightning plates. I've said it again. I don't know what the hell a lightning plate is, but apparently I want one. All right. And I think I showed you guys factorials, but I'm going to do it again. My calculator has an X exclamation point. Some calculators say PRB. And then it'll give you three options. It'll say n factorial, nCr, or nPr. And the order might be different, but it should show all three. The factorial one is the one that has an exclamation point. Five factorial is 5 times 4 times 3 times 2 times 1. Three factorial is 3 times 2 times 1. So you keep multiplying by a decreasingly smaller number until you get down to 1. There's a factorial way to do it with, it's not whole numbers, but that'll never be in this class. That's some fucking like advanced applied mathematics shit that I don't even know what I'm doing. Fuck all that. That's too hard. Something that's handy. So you would actually calculate this out and you would get a number. This is 6 down here. This is 120 up here. So you actually get a number. If I have 5 factorial over 3 factorial, I can write 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. And without using a calculator, I can find the answer really quick. The 3's cancel, the 2's cancel, and the 1's cancel. They all leave behind a 1. And I'm just left with 5 times 4, which is 20. Which is the same thing as 120 divided by 6. So, if you have some archaic fucking calculator that's like the size of a fucking toaster, and it's got buttons that are like bigger than my thumb. This is like my mom's fucking type of calculator, like super big. All it had was numbers and like plus, minus, multiply, divide, equal. That's all I had on her shit. Super big buttons for like, I don't know, someone's blind, I guess. You can still do this just by canceling stuff out. It's also worth noting that you can shortcut this by recognizing 5 factorial is the same as 5 times 4 times 3 factorial. Because that is 3 factorial. So if I do that, I don't need to write out the bottom. I could just leave it as 3 factorial. And now the 3 factorial cancels and I get 5 times 4 and it's quicker. I don't have to write down as much. So just write the bigger number factorial until you get to the smaller number factorial, and then you can cancel some shit out. September. I don't know. I don't know why that popped in. It's the date. That's got to be why. I didn't hear it today. The old song. Now we get to the good shit. Good shit. The nCr and the nPr. The reason why this PRB button, which stands for probability, has nCr and nPr and n factorial together is because n factorial is used in both of these things, as you're about to see. But I don't want to get ahead. Angel up here is fucking like right. She's up here. Oh, what the fuck? She's been writing down for fucking 20 minutes.
Something's happening and I don't know what it is.
Where are you?
Homework had me lost. I need to regroup. I'm good.
Are you caught up?
Almost. I'm on 5 at the bottom.
That one?
4, yes.
Okay. Okay. So let's start talking about what's going on in this chapter that's so stimulating. Permutations versus combinations. Permutation is nPr and combinations is nCr. It's named after the first letter. Oops. And the things that go in it. N is the number of distinct objects. R is the number of objects to be chosen or to be selected. That'll make more sense as soon as I get into like a thing. If you even want to have all the equations down at once, I normally do the equations one at a time, but the equation for nPr is n factorial over n minus r, and then we do that subtraction and do that factorial. And nCr is n factorial over n minus r factorial times r factorial. So it's really close to nPr, it just has an extra thing. That's a two-part. They were back to back. That's right. All right, so what the hell are these? I think I'm gonna start my the whole spiel with permutations, but I think it's easier to explain what combinations are first. Because then you'll be like, okay, permutations is not that. So combinations, think of a combination pizza. They even call them combination pizzas because I don't know, they're fucking great like that. They got like 6 or 7 toppings. You got some meats in there, some pepperoni, some onions, some fucking bell peppers, maybe some sausage. They got a bunch of toppings, right? Mushrooms is a common one. That is not a combination pizza topping. Each place is individual. Those are the common ones. You might get tomatoes on some places. Some of them do salami.
Yeah, there it is. I
Linguica.
I forgot about salami.
Linguica is a great fucking name. That's on there. The point of this is, I wasted a lot of time writing down toppings. Very few have Canadian bacon. On a combo?
Yeah, they have like a bunch of.
Get the fuck out of here. I don't know what you're eating. All right, combination pizzas. The point is,
You just don't see it.
doesn't matter what order the toppings are put on it. They put the toppings on. I mean, other than like sauce isn't considered a topping. You should be putting sauce on first unless you're some form of fucking heathen. No, I'm a heathen and I don't even fucking put sauce last. That's fucking crazy talk. Cheese is usually next, but it's not required. Some places put the meats and other shit on and cheese on top, and it kind of like seals everything in together. So it doesn't matter. Order doesn't matter. For combinations. And when it doesn't matter for nCr. Permutations, order matters. President, vice president, treasurer, secretary, like people in a club. Like there's a ranking system here. President's on top, they're the first person. But the one you're probably most familiar with is first place, second place, third place. Order matters. First place, second place, third place, or what I like to call a winner and two losers. Right? If you're in second place, sure, you get a silver medal at the Olympics, you get a lot of praise, but you're still a loser in that contest. Sure, you'll beat everybody else on the fucking planet, but except that one person that you just fucking lost to.
Not first or last.
You might as well be. Second place is just first place loser. So order matters. Really?
I know, I'm impressed. I can't believe it.
Anybody else still writing?
Yes.
Okay. See, you're over here fucking giving yourself a hand cramp, trying to not be the person that slows everybody down, and then fucking Johnny over here.
That I can help.
Johnny's got your back. He can help you like write slower. He's looking out for you.
You can change.
Well, thank you for your blessing.
You're welcome.
Let's talk about something. This is from my childhood. The trifecta. The trifecta in horse racing, and I assume other forms of racing, but I did this in horse racing, is you bet on first place, second place, third place. And you have to pick the right horse for the right place. Pick the horse's position correctly. That's a better way of saying that. So I grew up in Sacramento. That's where the state fair is, although like Tulare County Fair will be up there. In fact, they might have been up there a couple weeks ago. I don't remember when the state fair is. I know it's in summer. But it's done at Cal Expo. They got a racetrack. And my friend, when I was growing up, my friend's stepdad, he fed all the horses, so he was able to sneak us into the state fair all the time for free. Me and my brother were like, I don't know, 10 or 11. We were young. We didn't know what we were doing. And my mom had to work during the day. And my cousin was off work. She was in her, I don't know, 20s or 30s. We were teenagers, not even teenagers yet. We were young. My mom gave her some money, take us to the fair. And so we went to the back because it was free. And so you go and buy the horse races. And she decided, I'm gonna teach these young little whippersnappers a fucking lesson about gambling. I'm gonna show them gambling sucks. So it was like $2 to buy a trifecta ticket. I don't know how much money we each got. My mom gave her money for us, like maybe 20 bucks each. This was like 30, 40 years ago almost, maybe 35 years ago. 20 bucks went a lot. $2, she wanted to show us how bad gambling was and asked us to pick the trifectas. So we each bought one ticket. I didn't know anything about horse flesh. I couldn't tell you, you know, some of them you can look at the horse and you go, oh, he's got a broad chest, got good lungs, he's gonna have longer endurance. I look at his fucking hind legs, he's got strength, he's gonna fucking be faster. No, I fucking 10. I'm just looking at the names. And I fucking nailed the trifecta. I remember this distinctly because my bitch cousin didn't let me have any of that goddamn money. Plus, it didn't work. I don't think she kept any of it. She said, I'm going to take it home and give it to your mother. And I assume she did. I don't know. I got to assume the best of her. But we were out $2 each for the fair, and I should have had a lot more money. Nailing the trifecta is a good payday. It's like 50 to 1 at least, because you got to pick all 3 horses in the spot. Now, generally, like they have a good idea of who the top contenders are. So, like having like the mix of the top 4 or 5 horses has a lower payout on the trifecta than like picking the shit horses and placing them in the trifecta, and you'll get like 300 to 1 or some shit like that. Because that's only happening if there's a fucking sniper killing all the good horses. But I got it, and yeah, I didn't get paid. How does that relate to this lecture right here? Trifecta, I had to pick the order. Order matters. I don't remember what the horses' names were. I like D&D and fancy shit. I'm sure there was great fantasy names in there. Maybe fucking something about chocolate. I don't know. So you have to pick 3 places. Pick top 3 positions. I don't remember how many horses raced, but let's say there was 12 horses. I don't think it's ever more than 12 horses, but it might be. There's only so much room on a fucking track. The horses got to start out on width, and you can only have so many horses side by side. So n equals 12, and I am picking 3 horses. So that's 3. So in permutations, this is 3p. I already fucked it up. 12p3. nPr. So my n goes here. I got my p and my r. So the formula for nPr, since it was on another page, is n factorial over n minus r in parentheses factorial. I will have 12 factorial over 12 minus 3 factorial. Jackie's up here nodding about fucking trifecta and horse racing. Jackie's a fucking, I think she's a degenerate gambler. She's apparently I am too. I like taking my lectures to gambling spots. She's like, oh yeah, I can tell you all about fucking Texas Hold'em. I know all about fucking gambling on the trifecta.
Probably say craps too. Nice.
Oh yeah. We're talking about roulette later today. 12 minus 3 is 9. So 9 factorial. And using that little hint I was saying earlier, I will just write that lower top one in terms of the higher one. 12 factorial is 12 times 11 times 10 times 9 factorial. My 9 factorial is Cancer, and I'm left with 12p3 equals 12 times 11 times 10, which is 1,320. What this means is that of the 12 horses, all 12, not just like the good horses, but all 12, There are 1,320 ways to pick first, second, and third. So the probability of winning the trifecta, based on what I knew, just picking random names. Probability of winning the trifecta. Remember that it's number of outcomes. Number of outcomes that match. Number of good outcomes, let's say that. Good ways. Over total number. There is only one winning combination. There is 1,320 ways to pick them. And if you throw that in a calculator, it's 0.000. There's 3 fucking zeros after the decimal. 758. Or 0.076% chance. I didn't even have a 0.1% chance of picking that trifecta, and I got it. And she didn't let us have any money. She didn't even like give us an extra $20. Like, I'm sure it was like a couple $100. I always remember being stoked. I had video games in my head of what I was going to buy when we were walking back to cash the ticket, because I knew I was good at numbers back then. I could multiply. I knew how much money I was winning. I knew how much money I could spend this much at the fair. I could have this much. I could buy video games as much as I want, and I didn't get a goddamn dime. Not even the $2 back. She could have at least given me the $2 back. Right? That's permutations.
You were trying to be a master at stats as a kid.
No. That was pure luck on that. But like, I knew how to, like, if I spent $2 and it's like, or whatever it is, you multiply your wager by the output. I could do multiplication. I was only 10. Jesus. They start teaching times tables before 10 years old. You're in what? Fourth grade? Yeah. They start teaching multiplication tables before that. I knew how to multiply.
It might in like 3rd grade, I think.
Yeah, I remember like doing basic multiplication in 3rd grade.
Right.
I wish I could give my calculus students and my algebra students to do some fucking basic multiplication. All right, so that was permutations. Let's look at combinations. So combinations, order doesn't matter. Which one you pick on these is all dependent on whether or not order matters. Because the equations are slightly different. I'll rewrite the equation here. This is n factorial over n minus r factorial times r factorial. This one comes up so often that they just shortcut nCr. They call it n choose r. If you hear someone say n choose r, they are doing this thing right here. How many people I got sitting in here? I got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. A whole row of 5, 19, 20, 21, 22, 23. I got 23 people in here. You have 23 students present. What if I were to say, I am randomly picking 3 of you? To get a guaranteed A. If that sounds appealing to you, raise your hand. Not as many hands up as I thought. I think there's some people that didn't want to say it. I think most people want it. I wouldn't want it. I would rather earn the A, and I knew if I had the guaranteed A, I wouldn't, I would slack off. I would mean to earn the A, like still earn it anyways, but it'd be like, all right, got it. I can fucking do something else. I wouldn't want it, but I'm not judging you guys for raising your hand. This isn't your favorite subject. I wonder if I would have done this in art history class. If I would have taken the guaranteed A, I probably would have. I'm sure I would have there. All right, do you care if you are the first, second, or third person? Anybody?
No, doesn't.
No, doesn't matter. Even if you're, as long as you're one of the three. I didn't say the first person got like an A plus and the rest just got an A. I said everyone gets an, I get those three get an A, so you're getting the same price. No, order doesn't matter. That's what you should stop and do and think about whether you don't know whether the thing is a permutation problem or a combination problem. Go, doesn't really matter or what order I pick them in. nCr, we said above, for you guys, how many ways can I pick 3 people out of you if order doesn't matter? This is 23, choose 3. So 23 factorial over 23 minus 3 factorial times 3 factorial. That should say 23 right there. This gives us 23 factorial over 20 factorial over 3 factorial. And I'm going to do 3 times 2 times 1 because that will work. Let's see, the 20s cancel. 21 divided by 3 is a 7. And 22 divided by 2 is 11. This should boil down to 23 times 11 times 7. I don't know what that is, but I know how to find out because I've got a calculator. This number looks familiar. I think I counted the same number of students in my morning class when I did it with them. That's fucking crazy. Exactly 23 people showing up.
Stick that on another horse race.
Right? nCr is on my calculator. You can see it right there. If I can get it, if I can show it well. It's right there. So if I type 23 and then I hit nCr and then I hit 3, let's see if I can get the screen to show up. Not well. You can kind of see it at the top. Now you can't. It says 23, choose 3 up there. Fuck it. The lighting's bad. If I hit that in the calculator, oh, I gotta hit equal. If I hit equal, it says 1,771. As opposed to 23 NP, or doing it with permutations. That would give me 10,626. when order matters, there's a lot more outcomes. Because I have 3 angels in this class, and so if I picked all 3 angels. Like, there's only one combination of all 3 angels in here, if order doesn't matter. If order does matter, there are 6 ways to pick 3 angels in the sequence. So that is nCr. There are problems where we can use this kind of stuff. I think the other day in class, I don't know remember what numbers we used, but I'm gonna pick ones. Does anyone need this up longer? Okay. I think we talked about if we pick 4 people out of, I don't know, let's say 13 boys and 7 girls. What is the probability of getting at least 1 girl? So, how many different outcomes are in this thing? How many different girls can I pick? What are my choices? My options are going to end up being. I could pick 0 girls. I could pick 1 girl. I could pick 2 girls. I could pick 3 girls, or I could pick all 4. At least 1 means 1 through 4. Let's call that event E. So we want probability of E is our goal. Calculating this out, as you see when we get to 6.2, you'll find that this is fucking tedious. Well, we could do it today. No, it's tedious. We can't do it today. There's too many different combinations. But we had probability E plus probability of E complement equals 1. So I can get probability of E from 1 minus the probability of the event complement. And the event complement is easy. There's only one other outcome. So that's got to be event complement. This means all boys. 0 girls means all boys. This one is much easier to do. We don't need stuff from 6.2 to do this. So my probability of E is going to be 1 minus. Well, the first boy I picked, there's 13 boys out of 20 people, right? So that's the first boy. And then picking the second boy, we have 1 less boy and we've got 1 less person. And the third boy, another 1 less boy, another 1 less person. And we'll do this till we have 4 people. $13 times 12 times 11 times 10 divided by 20 divided by 19 divided by 18 divided by 17. This is 1 minus 0.147574819. That's all the decimal places my calculator shows. And so my answer is going to be 0.852. I'll just round to 3 decimal places for the final answer, or 85.2% chance of picking at least one girl. There's a quicker way of doing this with our combinatorics. Combinatorics, this bit right here I'm picking 4 boys out of 20. Well, I'm picking 4 people. 4 people first. Of the 13 boys, I'm choosing 4 of them. And of the 20 people total, I'm choosing 4 of them. If you do 13 choose 4 divided by 20 choose 4 in a calculator, you are going to get 0.147574819. So this is like total number of ways to choose 4 boys divided by the total number of ways to choose 4 people. What?
I heard that Pluto has more community.
All right, one more topic at 5.5, then we'll take a little 5-minute break, and then we'll do 6.1. And we got a full day. So 5.5, one last topic. We've been doing n distinct objects. Like, that's what we've been doing so far. What about non-distinct objects? Like the horses, they each had a name. Each topping had a different name for the topping. But what if I wanted to do like, let's do like, how can I arrange five white flags, four red flags, and 3 blue flags in a line? So W equals 5, R equals 4, B equals 3. I'm just writing down the numbers from there. And I'll draw 12 positions. 5, 6, 7, 8, 9, 10, 11, 12. All right, I'll go through the white flags first. I don't know, I could put one there. I could put one there. I could put one, I'll put one right next to it. Put one here. Maybe one right there. For the white flags, I had 12 positions to pick from, and I chose 5 of them. I did 12, choose 5 for white. Then I do my red flags. I can place 4 red flags. Let's put one there, there, and there. I had, let's see, I had 1, 2, 3, 4, 5, 6, 7 positions to choose from, and I got to place 4 flags. So I had 7 choose for red. Then along comes blue, and I got 3 blue flags, and I have exactly 3 positions to put them in. Blue didn't get any choice. So 3 positions and 3 pick, 3 choose 3 for blue. Now we're looking to see how many ways we can arrange them, so we should be able to multiply these. We can multiply them to find out. So 12 choose 5, I'm going to write it in terms of its factorials. That's my white one. My red one was 7 factorial over 7 minus 4 factorial times 4 factorial. And my blue one was 3 choose 3, 3 factorial over 3 minus 3 factorial times 3 factorial. I'll pause, give you a second to catch up. There's a lot of fucking exclamation points right here, going on here, right? We're gonna tidy up, cancel out some shit as much as we can a little bit. Down to a limit. I don't want to go down too far because it'll destroy what I'm trying to show you here. If I do that 12 minus 5, I get 7 factorial. And then if I do 7 minus 4, I get 3 factorial. And if I do 3 minus 3, I get 0 factorial. I don't think I told you what 0 factorial is. Fuck, this is what I meant to do when I was talking about factorials. I got excited. Quick sidebar. 0 factorial is defined to equal 1. Let's start circling and canceling out shit that goes away. I don't want to do that till everyone has it written down though, because I'm gonna be crossing off shit you're looking at. Well, this 3 factorial and this 3 factorial, they cancel out. Maybe I'll just circle. Things that go to 1. These two cancel each other out. 0 factorial is already 1. And I have a 7 factorial there and a 7 factorial there. I can cancel those out. Without going any further, I got that down to 12 factorial, 5 factorial, 4 factorial, 3 factorial. Is there any relationship between those numbers and what we started with? It's the number of the flags. What's the 12?
For the spaces.
Yeah, it's the total number of spaces, the total number of all the flags. This was for the 5, 4, and 3, but in general, if we have n items, from k distinct or from k groups, where the stuff in each group is identical. As identical members within. So like the white flag group, they're all the same color. They all look the same. The total combinations are they write it like this. They say n factorial for the main total. And then they put like n sub 1 factorial, n sub 2 factorial. And we're just multiplying these over until we get to the kth group, n sub k factorial. Where these n sub I are the number of objects in each group. In the ith group. Now, since I want to get 6.1 today, I'm not going to go over the lotto, but maybe we'll go over the lotto on review day. How do they calculate your odds of winning the lotto? How can you decide when the jackpot's big enough that it's a good thing? Let's take a 5-minute break. Stretch your legs, use the bathroom if you need to. All right, so we're starting chapter 6. Chapter 6 is on discrete probability distributions. Six point one, we will discuss the discrete random variable. Let's just throw down what you guys are going to want to use later. Angel, you definitely want to take a note of this. Stat crunch, you're doing stats, calculators, custom. Custom is at the bottom of the list. Everything else is listed alphabetically. And then they said, you know what? Let's put custom that starts with a C at the fucking bottom. All the way down, very fucking bottom. Like there's 20 things on the goddamn list, and they put it on the bottom. C's are like right away. The other thing you need to know, we'll use a lot in here, is E of X. E of X stands for expected value. It's really just the mean. And we are going to calculate that as the sum of X times P of X. So this section is called random variables. What is a random variable? Random variables in the stats circumstance are numerical measures of the outcome from a probability experiment. I'm going to probably put RV for random variable. RV means random variable. You can get tired of writing the words random variable and you're going to be happy. I said, let's use RV for random variable. Oftentimes we're looking at something like this. So my capital X, which I am using the Roman numeral X, Roman numeral 10, for because it's really hard to see in handwriting the difference between a capital and a lowercase. The capital X is the category of the outcomes. Lowercase x here is a specific outcome let's say from the different options. Since this is the options can be different and the outcome, the specific outcome I can choose is different. X is our random variable. For X to be a discrete random variable, blah, blah, to be a discrete random variable, its options should be countable numbers. Even decimals are fine if there's a fixed number of decimals. If we're looking at all the possible different outcomes between $0 and $1, there's 100 of them. They're all decimals, like 98 cents is 0.98 in terms of dollars, but it's still a countable thing. What was the other category of numbers that we had when we were talking in chapter 1 in the beginning? We had the quantitative numbers.
Qualitative and quantitative.
We had qualitative and quantitative, but quantitative broke down into discrete and something else. Continuous. Continuous is the other option. Continuous is going to be chapter 7. You guys ready for an example? Anybody need this up longer? Rock, paper, scissors. Does anyone in here not know how to play rock, paper, scissors? I fucking am worried about the day that I get a hand go up for that. Like, if I get a student that says, I've never played rock, paper, scissors, and they're not trolling me, like, their parents need to be shot or something like that. It's like, you've raised your child in way too much fucking isolation, too. This is like one of the earliest ways you've learned to pick how to settle a disagreement friendly, right? I want to go to this place for dinner. I want to go to this place. Rock, paper, scissors. This is for friends. If you're married, wife always wins. So let's say Angela and I play 5 games. I want to see what is the probability I win 3 or more. Winning 3 or more means I won best of 5, right? So in terms of what we're talking about here, I am tracking how many games I won. So the number of games I won is my random variable. This is the, well, let me just walk out through the example. How many different options can I have for this? Like, how many games can I win if we play 5 games? What are my different possible outcomes here?
5.
5, 4. I can lose them all. I'm gonna keep them in order. We'll do descending order here. Those are my possible outcomes. So big X here will be like, the name of the category is how many I won. In this case, I am looking for the probability that X is greater than or equal to 3. So this is a discrete probability model. Or I could make a discrete probability model if I did the whole damn thing out, because the number of wins is countable. Is a discrete number. What we have in this class, we're gonna be, at least this section, we're gonna be looking at a lot of probability distribution tables. Probability distributions are usually written as a table. Listing all possible outcomes. And their probabilities. I'm grading my exams for my calculus class. Never taught calculus 1 before, taught calculus 3, but not calculus 1. It's been a fucking bloodbath. There's like 36 students in there. I think maybe 28 took the test. I've only graded 9 of the 12 questions, but I'm already absolutely certain that only 2 of them got A's. One got 100%, and the next highest score was 90.5. And I finished their grading, their question, their test, even though the rest still have 3 questions. I normally do 1 question at a time. I finished those grading this right away because they were consistently not getting things wrong, except for very little. But one of them didn't get anything wrong. So I graded real quick. I wanted to see if I was going to actually get any A's, because every other page had -5, -6, -5, you know. And then I didn't finish grading the rest, but I looked through, like, skimmed pages. Every single other test had over 10% off, which means out of 28 people, only 2 A's and 1 barely an A at 90.5%. 0.5, 90.5. Half a point above 90%. It was a bloodbath.
That 100% is crazy.
100% means
That's great.
that the test was doable. She actually did better than I did.
That's an outlier. That 100%'s an outlier. Not even I would get it for someone coming.
Not even you.
Not even.
I didn't. I got to like question 11 and like she had a different answer than me. I'm like, there's no way she missed something that easy. It was like one of the easiest things on the test. And so I double checked my work and sure shit, I rushed. I'm not taking a test, so I just rushed through the answers. And I figure I will find the wrong answer as soon as either everybody's got a different answer than me and they all look the same, or I find the smart kid in the class and they show me where my wrong answer is. All right, probably let's keep going. That's a quick diversion. Let people finish writing. We're talking about the mean of a discrete random variable. This is stuff we're interested in for most of the stuff from here on. This actually has two possible setups. A, we have the actual data. B, we have summarized data. The actual data, we can compute it normally. It's X bar, since it's a sample. We've been doing stats, summary stats, columns. That's what we've been doing in StatCrunch to get ours. Summarized data, though, is usually what we have. This one, the actual data requires all the individual responses. But it gets you the actual mean. It's the actual mean. Summarized data, we're looking at the big picture. We're looking at mu of x, the population. This is going to be the sum of x times p of x. This is the theoretical mean. And if our sample size gets large enough, our sample mean approaches this theoretical mean. So like eventually x bar minus mu of x is about 0. They're that close. We just need a large enough n. I gotta ask, because my favorite squinter, does that help if I brighten it a little bit? Because I can't get you to fucking move to the front of the class where you can see better. Ooh, yeah, that's nice. That's warming. Since the mean value of a random variable mu of x represents what we expect to happen in the long run. We call it expected value. Because it's what we expect. It goes by E of X. Now, I wonder, let's see. Jackie, have you read any books that have the math on gambling? No, okay, not that bad yet. Yet, I'll fix you, you'll do it right. Math books are like the gambling world. Expected value is the most fucking important thing to them. It's how they make their money. And we're gonna see that in a second with roulette. Because expected, like you play roulette, you can win a lot in a single play, or you can win a little in a single play. But the house, in the long run, always wins. Otherwise, they wouldn't be in business. If the house in the long run lost, they'd fucking be out of money really quickly. I want to open a casino. I want to have enough money to open a fucking casino. Even if it's just a little card room. Get the fucking permission from the state. Be great. Because they always win. You just gotta win enough money to pay the employees and then you're fine. All right, let's take a look at some examples. I was just waiting for everybody to look like they were finished writing. Is everyone finished writing? Does anyone need that up longer?
Can you say yeah? I'll take a picture of the pop-up. Go ahead.
If you're still writing, go.
Go on.
Does anyone else need it up longer? All right. So this is pre-pandemic information. You'll see when you look at it, you'll be like, yep, this was pre-pandemic. They did a survey recording the number of movies streamed from Netflix in a month. And I wish I knew what year I got this data from, because like, I almost think it was like one of the earlier years of Netflix. So I'm going to make a little table. And I will have number of movies streamed. And it's the relative frequency of the outcomes. But we're going to treat it as the probability of picking that number of movies in the future. We talked about relative frequency and probability being closely related. They had 0, 1, 2, 3, 4, and 5. Now, I think this shit's a little bit easier to read if you put like little lines between every two. So like for 0 movies, this is the probability that X equals 0. And it was 0.06. The probability that big X equaled 1 was 0.58. And I'm going to go through this list. I'm just writing probability that X equals for all of them. And then I'll fill in the totals. It's 0.22, 0.10, 0.03, and 0.01. Does this meet the criteria of a probability model? There were two criterias. Probability that x equal the specific x is between 0 and 1. And the sum of all probabilities equals 1. Let's give everyone a chance to get caught up here. Been watching Billions with Paul Giamatti. Fucking love it. And normally I am not one for fucking drama shit. Like drama, like it's gotta be really good to keep me captivated, but I can like actually watch it without playing a video game or something else while I'm doing it. So I think it's on Showtime and we're watching it on Prime. So I think we must have Showtime on Prime. It's about Wall Street, hedge funds and shit like that.
David, what was the lightning bolt called again? Anything?
That
Yeah.
that is capital sigma. The lowercase sigma is the other one is that. So that's lowercase, that's uppercase.
Gotcha.
You know, Greeks had capital letters too. All right, so I can see looking at the probabilities that they're all between 0 and 1. Did anyone add those up? Because that's how we show that it's a probability model. You get 1.0 for that. All right, let's look at our expected value. It is the sum of x times p of x. So what we need to do is for each row, multiply x, which is our first column, times p of x, which is our second column. 0 times 0.06, that equals 0. 1 times 0.58 equals 0.58. 2 times 0.22 is 0.44. 3 times 0.10 is 0.30. 4 times 0.03 is 0.12. And 5 times 0.01 is 0.05. If we add all those up, that's our expected value. And you should get 1.49. So when this was written, the average household watched 1.49 movies per month. It's clearly an average. It's not a possible outcome. Or at least it's not a recorded outcome. I guess you could watch one movie and then 49% of another movie. I want to load up StatCrunch real quick and show you this table in there and using it. All right, I'm going to switch this over. Put in StatCrunch real quick, then we're going to do roulette and we'll be done. So I'm going to label these so they're easier to identify later on. X and P of X. This is 0, 1, 2, 3, 4, 5. 0.06, 0.58, 0.22, 0.1, 0.03, and 0.01. Here we're going to go stats, calculators, custom. So see it's at the bottom. Everything else is alphabetical there, but custom's at the bottom. It asks us for values and weights. And I'm going to write these down on the paper in a second, so they'll be in the notes. But values are your X and weights are your P of X. And I'll click compute. And it tells me my mean here. It even tells me my standard deviation. What's really neat is, I don't know if you can see it, but the 0 bar and the 1 bar are red. And right now it's telling me the probability that X is less than 1. Less than or equal to 1. Less than or equal to 1 means 0 and 1. And so like the red bars will show you what's being highlighted down here. If I say probability that X is greater than 1, greater than 1 is 2, 3, and 4, and 5, and they're down here. So it'll quickly find these for you, and the red shows you, like you can confirm visually that you have the right stuff. Now, granted, you could count these up by hand and go pretty quickly, and it wouldn't be a problem. But like, this is a convenient feature, and this shows up in a lot of the features of StatCrunch as we go on. All right, I'll write that down in a second. I want to show you guys the roulette table. For those of you that have never played roulette. In fact, that's the roulette wheel. It spins one direction. They flick a marble going the opposite direction. And eventually the marble is spinning against the wheel, it slows down and it falls and it lands somewhere in here in one of these bins. There's little metal ridges, so it falls in a bin. And there's numbers 0 through 36 listed, or 1 through 36 listed. And some wheels have 2 zeros, a green 0 and a double 0. And other wheels just have a single 0. So that's a table that has a single 0. And the one we're going to look at has double 0. You can bet on any single number and it pays out 35 to 1. You can bet on a row. You can bet on a group of 12. You can bet on 6 of them. You can bet on 4 by putting it in the corners. You can bet on 2 by placing the bet between them. You can bet on the color, red or black, odd or even. There's a lot of ways to bet. The more options you have for hitting your value, the less the payout is. Red and black are 1 to 1. They pay even money. So do odd and even. So let's take a look at a roulette probability distribution real quick. I wanted to show you the table. Oh, before I do, on our stats crunch with these stats calculators custom. So it's in your note. Values are your X and weights are your P of X. All right, talk about roulette. Every roulette game has 1 to 36. Every roulette game has a 0. Some roulette games have double 0, some of them. Most games have the double 0. The single 0 at a lot of casinos is the high roller table because the house doesn't have this big of a margin there. And so they want more money played so that they still bring in a lot of money. There's a lot of ways to bet. A single number bet, like say you bet on the number 7. Pays 35 to 1. When I get done with the roulette like distribution, I'll tell you how to read odds in terms of probability. That's for the real, how gamblers can fucking translate shit. So if we build a table, I want to look at the outcome. I either hit my 7 or I miss the 7. If I hit the 7, I make $35. I am up $35. So that will be this will be my X column. This is a numerical measure of that outcome. If I miss the 7, I lose $1. I don't even know if there are casinos in Vegas that have like $1 roulette tables. There's gotta be. I would think the minimum is 5, but there might be a cheap table. You can find it.
I couldn't find it.
She's like, I looked. All right, so the probability of X hitting the 7, there is one way to hit the 7 out of 38 options. There are 37 ways to miss the 7 out of 38 options. 36 numbers and then 2 green numbers is 38. So like 1 over 38 is approximately 0.0263. . So this is about 0.0263. This one is 0.9737. Now, when I do x times p of x, since we're talking about money, I'll just do 2 decimal places, 0.92. That's what I can expect to win for every dollar I play. Or that's my expected win in the long run. For every dollar played, I'll win 92 cents. If I multiply, that's doing 35 times 1 over 38. If I multiply -1 times negative 37 over 38, I get negative 97 cents. Which means my expected value is negative 0.05. Now, there's no way to lose 5 cents on a dollar bet, because that's not one of the outcomes. I either lose a dollar or I win 35, but it's what happens in the long run. That's not a lot, but they don't let you bet a dollar at a time. This is how much, so on average, you will lose 5 cents for every dollar you bet on roulette. And even though I just showed this for the single number outcome, if you do this probability distribution for every single possible outcome, like betting on odd or even, betting on a row, something like that, it comes out to 5 cents every single time. It's crazy. It's miraculous to me, but it's true. No matter what you play, you're losing 5 cents on every single bet for every single dollar. Doesn't seem like a lot, but like how much money goes through a roulette table in like a month at like a big casino in Vegas? Some people feel like if it's $10 million, I don't know. I know people that work at casinos. I know one that's a pit boss, but like at Chuck Chansey, I gotta ask him if they have roulette tables up there. He might actually know the answer to how much this is. If $10,000 are bet and it's 5 cents a pop, casinos bringing in 500 grand. That's some significant digits right there. That's a lot of cash. That's just saying 10 million. I don't know if it's 10 million. I suspect that a Vegas place it's higher, because they keep those things running as many hours as it can. And Vegas has that crowd to be 24/7. So odds, doing odds, 35 to 1 are called odds. 35 to 1. Another way they write this is 35:1. What this means is 35 ways to lose, 1 way to win. Or equivalently of that, which means there's a total of 36 outcomes. So if there were no green balls on the table, or green slots on the table, then the probability of hitting would be 1 out of 36, just like the payout, and it would be even money for the house. And they wouldn't do it because they have to pay their employees. If you see something like 3:2. Or 3:2. There are a total of 3 plus 2 equals 5 outcomes. So your probability that you're getting is 2/5. That's how you read odds. Now, I did have one more problem I wanted to do. It's on term life insurance policy. We're not gonna have time for it. If you watch the video from the other class, it's like the last 8 minutes. It's not that long. It's worth watching because I think there's a homework problem like it, and you'll see how it works. And I'll have that up. I gotta go home and upload the videos for this whole week tonight. I haven't uploaded any videos yet. I've been a slacker. Other than that, have a good evening. GTFO, gotta say it.